So let's start today's class. So let's start
So let's start today's class,
fundamentals of nano
Fundamentals of
quantum
Nano and Quantum
photonics.
Photonics.
So
So
this is the
this
last
is the last
class of this
class of
course,
this course,
and
and
this is the final
this is the
week in
final
which
week in
we will
which we will
tie together
tie
theory and
together theory and
application of nano
application
and
of nano
quantum
and quantum
photonics.
photonics.
In the
In
early
the
weeks,
early
we
weeks,
focused
we
on
focused on
conceptual
conceptual
foundations
foundations
with minimal
with minimal
mathematics,
mathematics,
and then we
and
introduced
then
the
we introduced the
mathematical formulation
mathematical
for
formulation
quantum
for
optics.
quantum optics.
And
And
so in
So
today
in
we will
today we
connect
will
all the
connect all the
descriptions
descriptions
regarding
regarding
statistics,
statistics,
quadratures, correlation
quadratures,
functions,
correlation
and
functions, and
uncertainty relations.
uncertainty relations.
So,
So
so in the
so
last
in
week
the
we
last week
derived the
we derived the
expression for the
expression
quantum
for the
harmonic
quantum harmonic
oscillator,
oscillator,
where we
where
express
we
the
express the
Hamiltonian
Hamiltonian
using ladder
using
operators.
ladder operators.
H is equals
H
to
is
h
equals
cross
to h
omega,
cross omega,
a degree
a
plus
degree
1 by
plus
2,
1 by 2,
where we found
where
out
we
that the
found out that
state
the
energy ground state
ground
energy
state
is
energy
equals
is
to
equals
half
to
h cross
half
omega.
h cross omega.
So,
So
and we can
and we
calculate
can calculate
the excited
the
state.
excited states.
So if we know
So
the
if
ground
we know
state,
the ground state,
if we know the
if
ground
we know the
state,
ground state,
if the zero
if
is
the zero is
known to us, then
known to
we
us,
can
then
find
we
out
can
the
find out the
nth excited
nth
state
excited state
using this
using
relation.
this
N is
relation.
equals
N
to
is equals to
a dagger
a dagger
power n
power n
upon n
upon
factorial
n
under
factorial
square root
under
under
square root
n
under
factorial,
n factorial,
and then
and
zeroth
then
state.
zeroth state.
So
So
classical harmonic
classical harmonic in
harmonic
classical
oscillator,
harmonic
we
oscillator,
defined a
we
mass
defined a mass
which was
which was
hanging and moving.
hanging and moving.
So
So
we saw that
we saw that
there was
there was
basically
basically energy oscillating between electric
magnetic
and
field.
magnetic field.
It doesn't
It
have.
doesn't have any. So
We saw that
we
photon
saw that
numbers did
photon
have
number state have
doesn't have any
doesn't have any
meaning
physical
that has
meaning
any
that has
position
any
associated
position
with.
associated with photon.
So basically, we
So
are
basically, we are
talking
not
about
talking
a
about
localized
the
photon.
localized
We will
photon.
talk. We will talk
We
about
are
a
talking
single
about a
photon,
single
and hence we
photon,
can
and hence
define
we
of
can define of
we can
we
define
can
number of
define
photons
number of
as a
photons as a
number state.
number state.
So we
So
will define
we will
number
define
operator
number
and
operator
number
and
state.
number state.
If number
If
operator,
number
if
operator,
number operator,
if number operator,
which is given by
which is
figure
given
A,
by a figure A,
will act on
will act on
number state,
number state,
it will give the
it will
number of
give the number of
photons
photons
in that particular
in
state.
that particular state.
So this
So
is we have
this
the
is we
eigenvalue
have the
equation,
eigenvalue equation,
and each
and
n
each n,
each number state
each
n
number
will
state n
correspond
will
to a
correspond
state
to a state
with n
with
photon
n
in that
photon
particular
in
state.
that particular state.
And
And
so number
so
state,
number states, we
using this
using
eigenvalue
this
equation,
eigenvalue
we can
equation, we
say
can
that
say that
number states are
number states are
eigenstates of
eigenstates of
Hamiltonian.
Hamiltonian.
So we can say
So we
that
can say that
number states
number
are
states are
a number
a
operator
number
acting on
operator
number
acting
state
on
will give
number
the
state will
number
give
of
the
photons
number
in
of
that
photons in
particular
that
state.
particular state.
So we can say
So
that
we
the
can say
zeroth
that the
state
zeroth
is
state is
vacuum
vacuum
state or
state
zero
or
photon state,
zero
one is
photon state,
photon
one is
state.
one photon state.
It says that quantized field
It
excitation
says that quantized field excitation
does not represent, does not
does
have
not
any position
represent, does
associated
not have any
with
position
the photons.
associated with the photon.
Then
Then
eigenstates are orthonormal.
eigenstates
So the
are
number states
orthonormal.
form an
So the
orthonormal
number
basis.
states form an
So in case
orthonormal
of
basis.
orthonormal
So
basis,
in
we
case
can
of the
write
orthonormal
n
basis, we can
prime n
write n
is
prime
equals
n
to Kronecker
is
delta.
equals to Kronecker
This is,
delta. So this is,
we can say,
we can say,
this is the
this
Dirac
is the Dirac
bracket,
bracket,
the
and
inner product of,
inner product
we
of,
can say that
so we can say
inner product of
inner product of
two wave function
two wave function
will give Kronecker.
will give Kronecker.
So
So
we can write
we can
this
write
if n
this if n
is equals to n
is equals to
dash,
n dash,
then n dash,
then n dash,
then this inner
then
product
this
will be
inner
1.
product will be 1, since
These
these
number states,
number states,
these number
sorry,
states
these
form
number states form an
orthonormal basis.
orthonormal basis.
And if
And
n
if
is not
n
equals
is
to
not
n
equals
prime,
to n prime,
then it will be
then
0.
it will be 0.
Now
Now
let's consider
let's consider
ladder operator operating on number state.
ladder operator operating on
We
number
want
state.
to,
We want to
so we found out that any quantum state of
So we
light
found out that any quantum state of light
can be expanded and
can be
as a
expanded and
superposition of
as a
these number
superposition
states.
of these number states.
Now we are considering
Now
that
we are
we
considering
are
that
applying the ladder
we are
operator
applying the ladder
which will
operator,
operate on a number
which
state.
will operate on a number state.
So A
So
n,
a n
A is the annihilation
is the
operator or lowering
annihilation
operator
operator or lowering operator
is equals to
is
Cn
equals to Cn
n minus 1.
n minus 1.
So, since
So,
A is the
since
annihilation
A is an
operator,
annihilation operator
lowering
or
operator,
lowering
we will
operator,
go
we
state
will go one
we will
state
jump
below.
we will go to the
We will go to
one
the
state below, and
one
similarly
state below.
in
And
case of
similarly,
air,
in
we
case of
will
air dagger, we will
move up one
move up
state
one
by one
state
state.
by one state.
So now we will take
So
the
now we will
conjugate,
take the conjugate,
both sides.
both sides.
So it will,
So
so
it
bra
will, so bra
cat will
cat will
interchange, A will
interchange.
convert into
A will
A
convert
dagger,
into A dagger
and Cn
and
star.
Cn star.
Now
Now
take the product of
take
these
the product of
equations.
these two equations.
Then n
Then
A
n
dagger A
A dagger A
is equals
n
to
is equals to
n minus 1.
n
Cn
minus
star and
1.
Cn
Cn
will give
star
you
and
the
Cn will
modulus of
give you the
Cn
modulus
square,
of Cn square
n minus 1.
n minus 1.
So we know that
So we know
A
that
is the
A dagger A
number
is the
operator.
number operator.
So n
So n
n
n
is equals to
is
Cn
equals to
square,
Cn square
Cn square
Cn square
n minus 1
n
n
minus 1
minus 1.
n minus 1.
So n minus
So n
1
minus 1 n
will
minus 1
give us
give
1.
us 1.
So n,
So n,
this n
this
will be
n will be
outside and this
outside and this n will
so
be 1.
n
So n
is equals to
is equals to
Cn
Cn
square.
square.
Now
Now
we can write
we can write
A
A
operating on n
operating on n
under root of
under
n
root of
n
n
minus.
n minus 1.
So when
So when
the
the
operator
operator
annihilation
annihilation
operator on
operator
the
will
number
act on the
state
number
n,
state n,
then it will
then
give
it
us
will give us
the
the
coefficient
coefficient
root n,
root
and we
n,
go
and
into
we will
one
go
state
into
down
one
n
state down
minus.
n minus 1.
Similarly,
Similarly,
if we will
if we
operate
will operate
the
the
similarly if we will
similarly if we
operate
will operate
the raising
the
operator
raising
A
operator
dagger
A
n,
dagger n,
we will get
we
the
will get the
n plus
n
1.
plus 1.
So
So
we will do in
we
the
will do
we
in
can
the we
follow
can
the same
follow the
process
same process
like
like
A
A
dagger
dagger
Cn plus 1.
Cn plus 1.
We will follow
We
the
will
same
follow the
process
same process
A
Na
is equals
is
to
equals to
n plus
n
1
plus 1
Cn star,
Cn star.
when we will
When we will
take the product
take the product n
A dagger
A dagger
n is
n
equals to
is equals to
Cn square
Cn square
n plus
n
1
plus 1
n plus 1.
n plus
Now
1.
A
Now
dagger.
A dagger
So
A.
we know
So
that
we know that
A
A
dagger
A dagger
is equals to
is
1.
equals to 1.
A dagger
A
minus
dagger
A dagger
minus
A
A dagger A is
1.
equals to
We
1.
can find out
So
the
we can
value
find
of
out the value of A dagger.
A dagger
A dagger is
1
equals to
plus
1 plus
A dagger A.
A dagger A.
So we will
So we
substitute
will
the value
substitute
of
the value of
N
N
A dagger A
A dagger A plus 1
is equals to
is equals
Cn.
to Cn square.
So we find
So
out
we
the
find
value of
out the
Cn
value of
square is
Cn square is
N plus 1.
N plus 1.
It means
It means
when A dagger
when
will
A dagger
operate on
will
number
operate
state,
on
it will
number
give
state,
the
it will give the
coefficient value N
coefficient
plus
value
1
N
and
plus 1
we
and we
will
will
move
move
to
to
the
the
1
one
state.
state up.
So now
So
now we
now
know that
we know that
H is equals
H is
to
equals to
H cross
H
omega.
cross omega.
I'm not using
I'm
the
not using
cat, it
the
is
cat, it is
like cap,
like cap, cap.
understood
It
that
is understood that these are operators.
so if we say
So
that
if we say that
A dagger
A dagger
A acting on
A
state,
acting on state N.
so we want to
So we
calculate
want
that
to calculate that
this formula H
this
is
formula
equals to
H
H
is
cross
equals to H
omega A
cross
dagger
omega
plus
A
1
dagger
by
A
2.
plus 1 by 2.
So now
So now
if A dagger
if
A
A dagger A
will act on N,
will act on N
is equals to
is equals to,
so when
so when
A
A dagger A,
A
so
will
when
operate
A will
N,
operate on
what
N,
will it give?
what will it give?
It will
It
root
will
10
root N
and the state will
and
be
the
N
state will be
minus 1.
N minus 1.
When A dagger
When A dagger will
will
up, up,
apply on this, it
apply
will give
on this,
you
it
N
will give you N
root of N.
root
A
of
dagger
N. A
A.
dagger A.
So it means A
So it
dagger
means
A.
A dagger A will be N.
So N
So N
operator will act
operator
on
will
number
act
state.
on number state. It will give us N.
So now
So now
if
if
Hamiltonian will act on
Hamiltonian will act on N
number state,
number state,
what it will give?
what it
H
will give?
cross
H
omega
cross omega
A dagger A
A
plus
dagger A
1 by
plus
2
1 by 2
apply on N.
apply on N.
It will give us
It will give us
N
N
plus 1 by
plus 1
2
by 2
H cross
H
omega
cross
N.
omega N.
It means
It means
En is
En is N
by
plus 1 by 2
H cross omega.
H cross omega.
So
So
from here we can
from
prove
here we
that
can prove that
number state
number state
is an
is
eigenstate.
an eigenstate of Hamiltonian.
And Hamiltonian
And Hamiltonian acting on
will give
number
us the
state will
total
give us the
energy of
total
the
energy
system.
of the system.
Then
Then
now we want to
now we want to
generalize
generalize
this
this
equation
equation
to find out
to
the
find out
nth
the nth
eigenstate.
eigenstate.
So
So when
if A
if
dagger is
A dagger is
acting on 0,
acting on
it's
0,
giving
it
us
is
1.
giving us 1.
If A
If
dagger is
A
acting
dagger is
on 1,
acting on
it is
1,
giving
it is
us root
giving
2,
us root 2,
2.
2.
Similarly, A
Similarly,
dagger
A
2,
dagger
A
2,
dagger 3.
P.
Now,
Now,
if A
If
dagger
a
4,
dagger 4,
then it will give
then it
us
will give us
root 4
root 4
and 4.
and
Now
4.
if I want
Now,
to
if I
find out
want to
this
find
fourth
out this fourth
eigenstate, what I
eigenstate,
will do?
what I
4
will
is
do?
equals
4
to
is equals to
1 by root
1
4
by root 4,
A dagger
a
3.
dagger 3.
Then
Then
A dagger 2.
a dagger 2. Similarly, I can write it as
1 by root
1
4
by root
3
4,
2
3,
1
2, 1,
A dagger.
a dagger 0.
So now
So now,
if we know the
if we
vacuum
know the vacuum
and
state
raising
and
operator,
raising
we can
operator,
construct.
we can construct any state.
So then we
So
have
then we
generalized
have generalized it to
n state.
n state.
So then
So
we
then, if we
say
can
that
say that
if we
if
know
we
the
know the
vacuum
vacuum
state, we
state,
can
we can
find out
find out
and
and
raising
raising
operator,
operator,
we
we can
construct
construct
any
any
state.
state.
So we
So
can
we can
generalize it.
generalize it.
N
N
state is
state is
equals to
equals to
A
a
dagger
dagger
n
n
upon
upon
1
1
root
root
n
में n
factorial
factorial
and
and
0th
0th
state.
state.
So now
So
we
now
can,
we can,
there are
there are
some
some
properties
properties
for the
for the
photon
photon
number
number state.
when
When
A
a
operator,
operator,
that is
that
the
is the
annihilation
annihilation
operator,
operator,
is
is
acting on
acting on
n.
n.
So
So
when
when
A will
a will
act on
act on
n,
n,
it will
it
give
will
us
give us
n
n
minus 1.
minus 1.
And the
And the
coefficient,
coefficient,
constant
constant
coefficient is
coefficient is
root of
root of
n.
n.
So
So we,
in the
in the
previous
previous
slide, we
slide, we
saw
saw
that
that
these are
these
the
are the
orthonormal
orthonormal
states.
states.
So
So
n is
n
not
is not
equals to
equals
n
to n
minus 1.
minus 1.
So then
So
it
then
will
it
give
will
us
give us the
0.
0.
Similarly,
Similarly,
for the
for the
raising
raising
operator,
operator,
if
if
A
a
dagger
dagger
will
will
act on
act on
n,
n,
it will
it
give
will
us
give
the
us the
n
n
plus
plus
1,
1,
n,
n,
n
n
plus 1.
plus 1.
So
So
again,
again,
we saw
we
that
saw that
it gives
it
us
gives
the
us the
Kronecker
Kronecker
delta,
delta,
which
in which if
n dash
n
is
dash is
not
not
equals to
equals to
n, it
n,
will
it
give
will
us
give
the
us the
0
0
value.
value.
So n
So
is
n
not
is not
equals to
equals
n
to
plus
n
1
plus 1
state,
state,
so it
so
will
it will
give us
give
the
us the
0.
0.
Similarly,
Similarly,
n
n
minus
minus
1
1,
A
a
operator
operator,
and n.
and n.
So when
So
A
when a
will
will
act on
act on
n,
n,
it will
it
give
will
us
give
the
us the
root
root
n
n
and one
and one
state
state
down
down
n.
n minus 1.
So now
Now
these
these two
states are
states are
equal.
equal,
So the
so the
result
resultant will be
root n.
root n.
Similarly,
Similarly, we can
find out
find out
for n
for n
plus
plus
1
1
that
that
if
if
A dagger
a dagger
will
will
act on
act on
n,
n,
we will
we will
move up
move
to
up
the
to the
one
one
state
state
higher.
higher.
So
So
n
n
plus
plus
1
1,
n
n
plus
plus
1
1,
and the
and the
coefficient is n
coefficient is n
plus
plus
1,
1,
it will
it
give
will
us
give us the
the root n
root n
plus 1.
plus 1.
So
So
these are
these are
about the
about the
expectation
expectation
values and
values
how
and
can
how
we
can we
calculate the
calculate the
inner
inner
products for
products
the
for the
ladder
ladder
operators.
operators.
So we
So
saw
we
that
saw that
number
number
state
state
represent the
represent the
discrete
discrete
energy
energy
levels of
levels
the
of the
quantized
quantized
field,
field,
and
and
these will
these will
represent
represent
the
the
exact
exact
photon
photon
counts.
counts.
But
But
since
since
there is an
there is an
uncertainty
uncertainty
relation
relation
between
between
delta
delta
n and
n and
delta
delta
phi,
phi,
if we
if we
have
have
the
the
exact
exact
photon
photon
counts, we
counts, we
have the
have the
undefined
undefined
phase.
phase.
So,
So,
and we
and we
saw
saw
that
that
in the
in the
previous
previous
classes
classes
that
that
photon
photon
number
number
state
state
doesn't
doesn't
represent the
represent the
minimum
minimum
uncertainty
uncertainty
state.
state.
that is
that
fixed
is fixed
amplitude and
amplitude and
uncertain phase.
uncertain phase.
So
So
coherent states,
coherent
which
states,
we will
which
discuss
we will
next, that
discuss
is the
next, that is the
superposition of number
superposition
state
of
and
number
it will
state
give us
and
the
it will
minimum
give us the
uncertainty.
minimum uncertainty.
So photon
So
number
photon
states
number states
are the
are
quantized
the
energy
quantized
eigenstates
energy
of light
eigenstates
field.
of light
It is
field.
the basis
It is
for
the basis for
describing
describing
all the
all the
quantum
quantum
optical
optical
states, and
states,
it is a
and it is
bridge
a bridge
between
between
the
the
harmonic
harmonic
oscillator
oscillator
theory and
theory
the
and the
quantum field
quantum field
quantization.
quantization.
So
So
next we will
next we will
consider
consider
we will
so
in the
in the
previous
previous
lectures we
lectures we
calculated,
calculated,
we say
we
that
say that
okay,
okay,
delta
delta
x1,
x1,
the
the
uncertainty
uncertainty
relation
relation,
delta
delta
x1 dot
x1 dot
delta
delta
x2 is
x2 is
greater than
greater
1
than
by
1
4,
by
but
4,
we
but we
didn't do
didn't
any
do any
derivation for
derivation
that.
for that.
So but
So
we
but
saw
we
the
saw the
values,
values,
we
we
talked
talked
about the
about the
quadratures
quadratures
and saw
and saw
relation
relation
between the
between the
position and
position and
momentum
momentum
operator.
operator.
So now
So
we
now we
want to
want to
find out
find
the
out the
relation
relation
between
between
the
the
position
position
momentum
momentum
and the
and the
ladder
ladder
operators.
operators.
So
So
we
we
have the
have the
value,
value of,
we saw
we
that
saw that
the
the
x1 is
x1 is
related to the
related to the
q,
q,
whereas the
whereas the
x2
x2
quadrature is
quadrature is
related to the
related to the
momentum.
momentum.
So
So
that will
that will
connect the
connect the
electric field
electric field
description to
description
the
to the
our
our
harmonic
harmonic
oscillator
oscillator
picture.
picture.
So we
So we
have the
have the
A
A
and
and
A dagger
A dagger
value in
value in
terms of
terms of
x and
x
p.
and p.
So A is
So A
equals
is
to
equals to A is
1
equals
upon
to
root
1
2 h
upon
cross
root 2
m
h
omega
cross m omega
x
m
plus
omega x
iota
plus
p,
iota p,
where A dagger is
where A
equals
dagger
to
is equals to
m omega x
m omega
minus
x
iota p.
minus iota p. Right?
Now
Now
I want to
I
find out
want
the
to find
value
out the
of
value of
A
A
and A dagger
and
in
A dagger
terms of
in
x
terms
and
of
p.
x and
So
p.
first of
So
all,
first of all,
I will calculate
I
the
will
value of
calculate the
x in
value of
terms
x
of
in terms of,
so
so
A plus
A
A
plus
dagger
A dagger
will give us
will
the
give us the
2m omega x.
2m omega x.
From this we can
From
find
this we
out
can
x
find out x is equals to
h cross
h
upon
cross upon 2m omega
A plus
A
A dagger.
plus A dagger.
Similarly, we
Similarly,
can find
we
out
can
the
find out the
value of A
value of
minus
A
A
minus A dagger.
to iota
To iota
px.
px,
Then we can
then
write
we
that
can write as
is equal
px is equals to
minus iota
minus iota
m omega is
m omega
equal to
squared by 2
A minus
A
A.
minus A
So
dagger. So we
we have
we
written
have written
the position
the
and momentum
position and momentum
in terms
in
of
terms
my
of
ladder
my
operator.
ladder operators.
Now I want to
Now I
write out
want to write out
my
my
quadratures x1 and
quadratures
x2 in
x1 and
terms of
x2 in terms of
x in
x
terms
in
of
terms of
ladder operators.
ladder operators.
So our
So our
quadratures
quadratures
x1
x1
is equals
is
to
equals
m
to
omega.
m omega.
So we
So
know that
we know
x1 is
that x1
proportional
is
to
proportional to
q and q is
and q
proportional
is
to the root
proportional
of
to the root
m
of m
into x.
into
So
x.
now we will
So
substitute
now we
the
will
value of
substitute the value of x.
m omega by
M
2h
omega by
cross 1
2h
by 2
cross 1 by 2
h cross by 2
cross
m
by 2
omega
m omega
a plus
A
a dagger,
plus A dagger,
which will give us
which
the
will give us
directly
the directly
a plus a
A
dagger. So
plus A dagger. So
x1
x1
is
is
just the
just
average
the average
value of
value of
and raising and lowering.
raising and lowering operators.
Similarly,
Similarly,
x2
x2
is equals
is
to
equals to
minus
minus iota
omega is
omega
crossed by
is
2
crossed by 2
a minus
a
omega
minus
which will
omega,
give
which will give
us
us
minus iota
minus
by 2
iota by 2
a minus.
a minus omega.
This is the
This is the
this is
this
the
is the
difference
this is the
between
difference between
the
the
eigenvalue,
eigenvalue of
the raising
the
of.
raising and lowering operator.
So now we
So
have
now
written
we have written
the
the
m-
m-
position and
position
momentum
and
in terms of
momentum in
ladder
terms of
operators
ladder
and
operators
x1
and
and x2
x1 and
quadratures
x2
in terms of
quadratures in terms of
ladder operators.
ladder
So
operators.
these are the
So
value
these
x
are the value
in
x
terms
and
of
p in
a
terms of a
integral.
and a dagger.
X is equals
X
to
is
h
equals
cross
to
by 2
h cross
omega
by
a
2
plus
omega
omega.
a plus
P
a
is
dagger.
equals to
P is
minus
equals to
iota
minus
h cross
iota h
omega by
cross
2 a
omega by 2 a
minus omega.
minus a dagger.
And quadrature
And
of
quadrature
operators, we
operators,
define
we
the
define
normalized
the normalized
quadratures. X1 is
quadratures.
equals to
X1 is
half
equals
a
to
plus a
half a
dagger,
plus a dagger.
and x2 is
And
equals to
x2 is
minus
equals to
iota by
minus
2
iota by 2
a minus a
a
dagger.
minus a dagger.
So
So
the x2 will
the
represent
x2
the
will represent
amplitude
the
quad,
amplitude
x1
quad
will represent
x1 will
the
represent the
amplitude quadrature,
amplitude
that is the
quadrature,
in
that is
phase
the in
component,
phase component,
and x2
and
is the
x2
phase
is the
quadrature.
phase quadrature.
Because of iota,
Because
it
of
will
iota it
represent
will
the
represent
minus
the
iota, it will
minus iota,
represent the
it will
out of
represent
phase
the out of
component.
phase component.
Next,
Next,
we want to
we want to
we want to
we want to
calculate
calculate
the value of
the value of
sorry, we want to
sorry, you
calculate the
want to calculate
commutator
the
x1
commutator
x2.
x1 x2.
To calculate
To
the
calculate
commutator
the
x1
commutator
x2,
x1 x2,
it is
it is
x1 x2
x1 x2
minus x2
minus
x1.
x2 x1.
So x1
So
x2
x1 x2
we will write in
we will
terms of
write in
ladder
terms of
operators,
ladder
that is
operators,
minus
that is
iota by
minus
4.
iota by 4.
A plus a
A
dagger,
plus a dagger,
a minus a
a
dagger,
minus a dagger,
which is equals to
which is
minus
equals to minus iota by 4.
a
A
a
a
minus a
minus
dagger
a dagger
plus a dagger
plus
a
a dagger a
minus a dagger
minus
a.
a dagger a dagger.
Okay. Now when
Okay.
we solve
Now when we
the
solve the
x2,
x1 x2,
similarly you can
similarly
write
you can
x2
write
x1
x2 x1
is equals to
is
minus
equals to
iota by
minus
4
iota by 4
a
a
plus a
plus
dagger
a dagger
minus a dagger
minus
a
a dagger a
minus a
minus
dagger a.
a dagger a dagger.
So we will
So we
take
will
the iota
take
by
the
4
iota by 4 common.
a
a
a dagger
a dagger
minus a dagger a
minus a dagger a
plus a
plus
because
because
a
a
will cancel out
will cancel out
a dagger
a dagger
a dagger a dagger will
a
cancel
dagger
out.
will cancel
We
out.
will have the
We will have
fourth
the
term,
four
these
terms,
two and
these two and these two,
these two,
these two,
these two.
these two.
A
So
dagger
A
minus A
dagger
dagger
minus A dagger
A dagger
A dagger
minus A
minus
dagger
A
A.
dagger A.
It will give us
It
the
will give
iota
us
by
the
2
iota by 2
A dagger
A dagger
minus A dagger
minus
A.
A
So this
dagger
is
A.
the
So this is the
so this is
so
iota
this
by
is
2 because
iota
this
by
is the
2 because
number
this is the
operator.
number
A
operator.
dagger is equal
A
to
dagger is
1.
equals
So
to 1.
x1
So
x2 is
x1 x2
iota
is
by 2.
iota by 2.
So now
So
we
now
know that
we know that
if the two
if the two
quantities do not
quantities do not
commute, it means
commute,
there
it means
exists an
there exists an
uncertainty
uncertainty
between them.
relation between them.
If it will be
If
0,
it will be 0,
then these
then
two
these
quantities
two
commute and
quantities
we can
commute and
find
we
out
can
the
find
exact
out the
values
exact values
at the same
at
time.
the same time.
So now we will
So now we
calculate
will
the
calculate the
uncertainty relation.
uncertainty relation.
So
So
in the general
in the
form,
general
for
form,
any two
for any
operators,
two operators,
delta
delta
A square,
A square
delta B square
delta
is
B
greater
square
than
is
1 by
greater than
4
1 by 4
modulus of
modulus of
expectation
expectation value of the
value of these
commutation
two
of these two
operators by
operators
4.
by 4.
So if we know
So if
that
we know that
the x1 and
the
x2
x1 and x2
is equals to
is
iota
equals
by
to
2, we
iota
can
by 2,
apply
we
on
can
this
apply on
delta
this. So
x1
delta x1
square,
square
delta x2
delta x2
square
square
is greater
is
than
greater than
1 by 4.
1 by 4.
So what is the
So what is the
commutation value?
commutation value is
Iota by
iota
2.
by
So
2.
iota
So
by
iota by
2
2
product.
product.
That is
That is
1 by is common.
1 by is
There is
come.
modulus
There is
also.
modulus also.
So into 1
So
by
into 1 by 4.
so it
So
means
it means
1 by 6.
1 by
So
16.
now
So
delta
now delta, if it is 1 by 16, then
delta x1
delta
delta
x1
x2
delta
greater
x2
than
is
1
greater
by
than
4.
1 by 4.
This have already
This have already
calculated in this, but
calculated in
we
this,
now we
but
have
we now we
calculated
have
using the
calculated using the
ladder operator.
ladder operators.
This is the
This is the
uncertainty relation
uncertainty relation
for x1
for x1 and x2 quadratures.
So next is
So next is, what is the physical
so
meaning
we
of
saw
this?
that
So we saw that
quadratures behave
quadratures
like
behave like
position and
position
momentum.
and momentum.
The
The
non-commutation introduces
non-commutation
the
introduces
fundamental
the
quantum
fundamental
noise,
quantum noise,
and
and
if the
if
commutation
the
relation,
commutation relation,
if the
if the
uncertainty is
uncertainty is
existing,
existing,
then impossible
then
to measure
impossible
these
to
two
measure these
quantities
two quantities precisely
simultaneously.
simultaneously.
And this is the
And
basis
this
of
is the
the
basis
squeeze
of the
light
squeeze
and
light
quantum
and the
limit of
quantum limit
detection,
of
which is
detection, which is
analogous to
analogous to
the Heisenberg
the
uncertainty
Heisenberg
relation,
uncertainty
delta x
relation,
delta
delta
p
x
is
delta
greater than
p is greater than
equals to h
equals
cross
to
by
h
2.
cross by 2.
Next, we will
Next, we
calculate
will
the
calculate
vacuum
the
state
vacuum state
uncertainty.
uncertainty.
Uncertainty limit in the
Uncertainty
vacuum
limit in
state.
the vacuum state.
So in the
So in the
quadrature, how can
quadrature,
we
how
represent
can we
the vacuum
represent the
state
vacuum
when there
state
is no
when there is no photon,
right? So
right? So
this is delta
this is
x1
delta
is equals to
x1 is
1
equals
by
to 1 by 2.
this is delta
This is
x2
delta x2
equals
is
to
equals to 1 by 2.
so we define
So
the
we
x1
define the
and x2
x1 and x2 in terms of the ladder operators.
x1
x1 is
is
equals to 1 by 2 a
equals
plus a dagger, where
to x2 is equals
x2 is
to
equals
minus
to
iota by
minus
2 a.
iota by 2 a minus a dagger.
Then we want to
Then we want to
calculate
calculate the
what is the
what is the
expectation value for
expectation
a
value
vacuum
for a
state.
vacuum state.
Like what is the
Like what is
expectation
the
value? What
expectation
is
value? What
the
is
expectation
the
value of
expectation
x1
value of
for a
x1
vacuum
for
state?
a vacuum state?
So
So
if we want to
if we want
calculate
to calculate the
uncertainty limit,
uncertainty limit,
if we want to
if we
calculate
want
the
to
value
calculate the
of
value of
delta x1,
delta
which
x1, which
in the previous
in the
lecture we
previous
wrote
lecture we
directly.
wrote
Now we
directly.
want to
Now we
prove
want to
that
prove that
is it really
is it
coming
really
delta
coming
x1
delta
value.
x1 value?
So that's why.
So that's why.
So
So
delta
delta
x1.
x1,
If I want to
if I
calculate the
want to
delta
calculate the
x1
delta
square,
x1
it will
square,
give
it
us
will
the
give us the
expectation value of
expectation
x1
value of
square
x1 square
minus
minus
expectation value of
expectation value of
x1, the
x1,
whole square of
the whole square
expectation
of
value of
expectation
x1.
value of x1.
So now we want to
So now we want to calculate for
ground state if we
ground
want,
state.
are
If we are
calculating
calculating
the expectation
the
value of
expectation
x1.
value of x1,
So it will be
so it will
half
be half
0
0
a plus
a plus
whatever
a dagger
0.
0.
So half
So half
0 a
0 a
0
0
0
0
whatever.
a dagger 0.
So now when
So now
a will
when
act
a
on
will
0,
act on 0,
it will give us
it
0
will give us
since
0
0 is the
since
ground
0 is the
state.
ground state.
It's
Now
the annihilation
it's the
operator. So
annihilation
there is
operator.
no
So
state
there is no
existing
state
below the ground,
existing
so
below
it
the
will give
ground
us
state. So it
0.
will give us 0.
And when a dagger
And
will
when
act
a dagger will
on
act
0,
on 0,
so what it will
so
give?
what it will give?
0,
0,
a dagger will
a dagger will
1.
1.
So now these
So
states
now
are
these states are
orthonormal, that's why it will
orthonormal.
give us
That's why it
the
will
0.
give us the 0.
So the
So the
expectation value of
expectation
x1
value
is
of x1
0
is
for the
0
ground
for
state.
the ground state.
So now
So
the
now
quadrature
the
x1
quadrature
is related to
x1
the
is related to the
electric field.
electric
So
field.
if we take
So if we take
an average
an
electric
average
field in
electric
vacuum,
field
it will
in
give us
vacuum,
the
it will
0.
give us
Now
the
we want
0.
to
Now
calculate
we
the
want to
expectation
calculate the
value of
expectation
x1
value of
square.
x1 square.
So x1
So
square 1
x1
by
square
4,
1 by 4
0,
0
a plus
a
a
plus
dagger,
a dagger
a plus a
a
dagger,
plus a dagger
0, which
0,
will give
which
us
will
1
give
by
us
4,
1 by 4
0,
0
a
a
plus a
plus
dagger,
a dagger
a dagger,
a dagger a.
So now
So now
if 2
if
times
2
a will
times
apply, it
a will
will give
apply,
you
it will
2,
give you
so then
2. So then it
orthonormal 0.
orthonormal 0.
Similarly,
Similarly, a
a
will
0.
operate as 0.
Now when
Now
a will
when
operate
a
on
will
0,
operate on
it will
0,
give us
it will
also
give us
0.
also 0.
So the only
So
term
the
is
only term is
0,
0
a dagger,
a dagger
0.
0.
So it will give
So
us
it will
1
give
by
us
4.
1 by 4.
Okay. So
Okay.
now we
So
found
now
out
we
that
found out that
delta x
delta x
is equals
is
to
equals to
x1 square
x1 square
minus
minus
x1,
x1
which
square,
is 1
which is 1 by 4
under root
under root
delta x
delta
equal
x
to
is
1.
equals to 1 by 2.
Similarly,
Similarly,
delta x2 is
delta
also
x2 is also 1 by 2.
1. Hence, prove
Hence,
that
prove that
these
these
uncertainties delta
uncertainty
x1
delta
is equal to
x1 is
1 by
equals to
2
1 by 2
and delta
and
x2 is
delta
equals to
x2 is
1.
equals to 1 by 2.
And the product
And the
delta
product
x1
of
or
delta
delta
x1 and
x2
delta x2
is equal
is
to 1 by
equals
4.
to
That
1 by 4.
represents the
That
minimum
represents the minimum
uncertainty states.
uncertainty
And
states, and
vacuum
vacuum
fluctuations will exist
fluctuations will
even when
exist
the
even when the
electric field is 0.
electric field is 0.
We
So
saw that
we saw
average
that
of electric
average of
field is
electric
0,
field is
but
0, but
since there
since there
are the
are
vacuum
the
fluctuations.
vacuum fluctuations.
Next is we
Next
want to
is we want to
calculate the
calculate the
uncertainty limit for
uncertainty
the
limit
number
for the
state.
number state.
That is the
That
photon
is the
number state
photon number
Fock
state,
state.
Fock state.
So
So
similarly, what was
similarly,
the
what was the
now
so now
for the number
for the
state
number state
we have the
we have the
x1.
x1.
So number states
So
are
number states are the not the minimum uncertainty state.
the 0
This 0
and
and this is the
length.
length.
So we want to
So we want to calculate the
calculate delta x1.
delta x1 again.
So this time we will
So this
try
time we will
with
try with
x2 and
x2 and
x2 and
x2 and
minus I by
minus I
2
by 2
and
and
a minus
a minus a dagger
n.
and
So
so
and
and
this will give us
this will give us 0.
so
This
again
so again
n
and
x2
x2
is 0.
is 0.
Now
Now
expectation value of
expectation
x2
value of
square
x2 square.
minus 1 by
Minus 1
4
by 4 and
a
a
minus
minus
a
a dagger
minus a
minus a dagger a
minus
minus
a.
a dagger a dagger.
So again
So again
this quantity
this
will give us
quantity will
0,
give us
this
0,
quantity
this
will also
quantity
give
will
us
also
0.
give us 0.
So we are
So
left
we are
with
left with
minus 1 by
minus
4.
1 by 4.
We can common
We can
out
common it out
minus,
minus,
take outside
take
minus sign,
outside
that will
minus
be
sign, then
plus
it will be plus
n
n
plus n.
plus n.
So it will give
So it
us
will give us
1 will give
one will give
a dagger is
a
number
dagger is the
operator, it
number
will
operator.
directly
It will
give us n
directly give us n
and a dagger
and a
is
dagger a.
so
So
it will give us
it will give us
n,
n
it will give
and
us
it will give
n
us
plus
n
1
plus 1
n plus
n
1
plus 1
It will give us
and it will give us n.
so we will write
So we will write
plus
n
1
plus
plus
1
n.
plus n.
So it will
So
give
it will give us
us
2n plus 1, 4.
so
So
now delta
now delta x2
is equals
is
to
equals to
under root of
under root of
2n plus
2n plus 1
by 2,
by
which is
2,
also
which
equal
is
to
also
delta
equal to
x1.
delta x1.
And when we
When
calculate
we calculate
the
the
uncertainty relation
uncertainty
delta
relation
x1
delta
delta
x1
x2,
delta x2,
delta x1
delta
delta
x1
x2
delta x2
equals
is
to
equals to
2n plus 1
2n
by
plus
4
1 by 4
is equals to
is
1
equals
by
to 1 by 2
n plus 1.
n plus 1 by 2.
So if
So
n is
for
equal
n
to
is
0,
equals to 0,
we are getting
we are getting delta
x1
x1
delta x2 is
delta
equals to
x2 is
1 by
equals to 1 by 4,
4, which is the we can
which is
say
the
that
we
the
can say that the
foreground state.
foreground state,
It is the minimum
it is the
uncertainty.
minimum.
So in
So
general,
in
photon
general,
number is
photon
state
number
is
is
not the
state is
minimum
not the
uncertainty
minimum
state, but for
uncertainty
the
state, but
ground
for the
state,
ground state,
it has the minimum
it has the minimum
uncertainty state.
uncertainty state.
And for n is
And for
equals
n is
to 1,
equals to 1,
3 by 4.
3 by 4,
That is
that is
for any
for
other
any
state
other state
with n
with
greater
n
than 1,
greater than 1,
it doesn't have
it
the
doesn't have the
minimum uncertainty.
minimum uncertainty state.
So what is the
So what is
conclusion?
the conclusion?
The delta
So
x1
delta
equals
x1 is equals
expectation value
expectation value of
is
x1 and
0 for
x2 is
the
0 for the
number state.
number state.
Variance is equals
Variance is
to
equals to
2n plus 1 by
2n plus
4,
1 by 4,
and the
and the
delta x1.
delta x1.
So the
So the
uncertainty
uncertainty is
is
in the
within 2n
region
plus
within
1 by
2n
4
plus 1 by
under
4
root,
under root,
and the product
and the
uncertainty product
uncertainty
is 1
product
by
is
4
1
2n
by
plus
4
1.
2n plus 1.
For the n is
For
equals
the
to
n is
0,
equals to
we will
0,
have the
we will have
vacuum
the
state,
vacuum
that is the
state, that
minimum
is the minimum
uncertainty state, but
uncertainty
for n
state,
is
but for
greater
n
than
is greater than
0
0
or equals to
or
1,
equals to 1,
it will give us the
it will give
non
us the non
photon state doesn't
photon
have the
state
minimum
doesn't have the
uncertainty.
minimum uncertainty state.
So as
So
n
as n
increases,
increases,
uncertainty will
uncertainty will
increase
increase
in the number,
in the
and the
number,
phase will
and the
become
phase will become
indeterminate.
indeterminate.
So we can say
So we
that the
can
for n
say
is
that the
equals
for
to
n is
0,
equals to
number
0,
state is in
number
the
state is
vacuum.
in the vacuum state.
Now the
Now
question
the
comes,
question comes,
why
why
the
the
expectation value of
expectation
x1
value of
is equals
x1
to
is
0
equals to 0
for a billion
for
number
a billion
of
number of
photons.
photons.
So photon
The
number state
photon number states
cannot represent
cannot
a classical
represent a
electric
classical
field.
electric field.
So no
So
single
no
photon
single
number state
photon
can
number state
represent
can
a classical
represent a
electric
classical
field, and we
electric
will
field, and
have
we
to
will
consider
have
a
to consider a
superposition of
superposition of
photon number
photon
states.
number states.
So the note
So the
is
note is
no single
no
photon
single photon
In numbers,
in number
now
state. So
what is
now,
the need of
what is the
coherent
need of
state? We
coherent state?
define
So
the
we define
coherent
the
state as
coherent
the
state as the
minimum
minimum
uncertainty state
uncertainty state
with the length
with the length
by
given by alpha.
we can define
We can define the alpha
is equals to
is equals to
x1 plus
x1
x
plus iota x2
in terms of
in terms of amplitude and
phase
phase
exponential
exponential
iota phi.
iota phi.
So now we can
So now we
write
can write
in terms of
in
state
terms of
is
state is
alpha is equal
alpha is
to
equals to
exponential
exponential
minus
minus
alpha square by
alpha
2
square by 2
summation of
summation of n is
0
equals
to
to 0 to infinity
alpha
alpha
n upon root
n
n
upon root n
factorial.
factorial n.
So now this
So now
alpha
this
n
alpha n
by root n
by
is the
root n is
coefficient
the
associated
coefficient
with each
associated with
state,
each state,
and
and
it represents
it
the
represents the
superposition of number
superposition of
states
number
where the
states where the
exponential minus
exponential
alpha
minus
by
alpha
2 is
square
the
by 2 is the
normalization constant.
normalization
So
constant.
we can write
So we
any
can
state
write any
as a
state as a
superposition
superposition
of
of
number states. Suppose
number
we
states.
have
Suppose we have sine n is equals to
C naught.
c naught.
So C naught is the
So c naught is
coefficient
the
for the
coefficient
zeroth
for the zeroth
ground state. C1
ground
is
state,
for the
c1 is for the
first state,
first state,
and like this. So we
and
can
like this. So
write
we can write
alpha.
it
Suppose this
alpha.
is
Suppose this
alpha.
is alpha.
Alpha
Is
we can
equals
write
to, we can write
n is equals to
n is
0 to
equals to 0 to
infinity
infinity
Cn and
cn and
now
now
we will
if you will
so
so
if we are
if we
applying
are
H
applying
on
h
alpha,
on
it is not
alpha, it is
given
not
as
given
Cn.
as c
Means
alpha. It
alpha is
means
not an
alpha is not an
eigenstate
eigenstate of
of H,
h,
but alpha is an
but alpha is an
eigenstate of
eigenstate of
annihilation operator. We
annihilation
saw in
operator.
the
We
first
saw in
slide
the
A
first
alpha is
slide a
equals
alpha
to
is equals
C
to c
n is 0
n is 0
to
to
infinity
infinity
alpha n
alpha n
root
root
factorial
factorial
a n.
a n.
So it will
So
give us
it will
the
give us the
C
c
n 0 to
n 0 to infinity
alpha n.
alpha n.
So when A
So
will
when a will
apply
apply on n, it will give you
n
n
minus
n minus
state,
1 state,
which we can
which we
write
can write
alpha C
alpha c
n is equal
n
to
is
1
equals
to
to 1 to infinity,
1
and
n
alpha
minus
n
1
minus 1
n minus 1
n minus 1
and state
factorial
n
and
minus
state
1.
n minus 1.
So
So
we can say
we
that
can say that
for n is
for
equals
n
to
is
n
equals
plus
to
1,
n
it
plus
is
1,
a
it is a
coherent state.
coherent state.
And
And
A is
if
actor
A
on
is
alpha,
actor on
it will
alpha,
give
it
us
will
alpha
give us
alpha.
alpha alpha.
It means
It
alpha is
means
an
alpha is an
eigenstate.
eigenstate of A.
So in number
So
states,
in number states,
expectation value of
expectation
E
value
was
of
0
E
for
was
even
0
for
for
large
even
n.
for
It
large
means
n. It
it is a
means
not
it is a
classical
not
thing. So
classical thing. So
that's why we say
that's
that
why we
no
say that no
single photon number
single
state
photon
can
number
represent
state
a
can
classical
represent a
electric
classical
field. So we
electric
have
field.
to
So we have
consider a
to consider a
superposition of
superposition of
photons.
photon number state.
So here we
So
have
here we have
represented a
represented a
superposition with
superposition
Poissonian
with
photon number
Poissonian photon
distribution,
number
and we saw
distribution,
that
and we
alpha
saw
is.
that alpha is.
So what is the
So what
properties
are the
of the
properties
coherent
of the
state
coherent
alpha?
state
So alpha
alpha?
is
So
not an
alpha is not
eigenstate
an
of
eigenstate of
Hamiltonian H,
Hamiltonian H,
but it is
but
an
it is an
eigenstate of
eigenstate
annihilation
of
operator.
annihilation operator.
And then
And then
when we will
when we
apply
will apply
A dagger on
A dagger on
alpha,
alpha,
it will give
it
us
will give us
alpha alpha
alpha
star.
alpha star.
Okay,
Okay.
so
So
alpha
alpha
dagger
A
A,
dagger A
alpha
alpha
is equals to
is equals
alpha
to
alpha
alpha
star,
alpha star
alpha alpha.
alpha alpha.
So now A
So
dagger
now
A
A dagger A is the
number of craters,
number of crater,
which will give us the
which will give
number
us
of
the
photons,
number of photons.
and we saw
And
that
we saw that
n bar
n
is
bar
equals
is
to
equals
alpha
to
square,
alpha
so that
square,
we can
so
write
that we can
delta
write
n
as
is
delta n is n
bar.
bar.
So from this
So
we can
from this
say
we
that
can say, so
alpha,
where
what was the
alpha,
alpha?
what was the alpha?
So alpha is the
So
length.
alpha is the length of phasor.
Let me spell
Where we
this.
saw this.
Okay, and n is
Okay,
the
and n
average
is the
number of
average
photons.
number of
So what
photon.
is the
So what is
conclusion
the
there? So
conclusion there? So
we
we
constructed this
constructed this
equation,
equation,
that is
that is
alpha is
alpha
equals
is
to
equals to
exponential.
exponential.
So this
So this
equation
equation,
as a
as a
superposition of
superposition
all
of
these number
all these
states
number
also
states,
follows the
also follows the
Poissonian
Poissonian
statistics.
statistic.
We also knew
We
that
also knew
earlier
that
that the
earlier
coherent
that the
state has a
coherent state has
Poissonian
the Poissonian
statistics, but
statistics,
now we
but now we
proved it
proved it
by considering
by
the
considering the
superposition of all the
superposition of
states.
all the states.
So now
So now
we want to
we want
calculate
to
the
calculate the
uncertainty of the
uncertainty
coherent
of the
state. We
coherent
will
state.
take
We will
10-minute
take
break
10
here.
minute break
We will
here.
continue.
We will continue.
So now next
So
we
now
want to
next we
calculate
want
the
to
uncertainty
calculate the
of the
uncertainty of
coherent
the
state.
coherent
So we
state. So
calculated
we
the
calculated the
uncertainty between the
uncertainty
photon
between the
number state,
photon number
vacuum
state,
state, now
vacuum state,
coherent
now
state.
coherent state.
So now
So now
we wrote that
we
x1
wrote
in
that
terms of
x1 in
alpha
terms of
plus alpha,
alpha plus
1
alpha,
by 2 alpha
1
plus
by 2
alpha
alpha
star.
plus alpha star.
That is,
That is,
so to
so
calculate
to
the
calculate
uncertainty,
uncertainty,
so we
so
calculate
we calculate alpha
x1.
x1.
So
So
1 by 2
1 by 2
alpha
alpha
a alpha
a alpha
plus
plus
alpha idagger,
alpha idagger
which
alpha,
is
which is
1 by 2
1
alpha
by 2
plus
alpha
alpha
plus
star.
alpha star.
So now
So now
we got the
we
value.
got the value of x1.
We can write in
We
terms
can
of
write in
cos phi or
cos phi or
sin phi also.
sin
So
phi also. So
we know that
we
alpha
know
is
that
equals to
alpha is
modulus
equals
of
to
alpha
modulus
and
of alpha
associated
and
phase is e
associated phase
iota
is
phi.
e iota
Similarly,
phi.
alpha
Similarly,
state
alpha stay
star is E
star
minus
is E minus alpha phi.
so x
So x1
1 by 2
1 by 2
alpha common
alpha common,
and then E
and then E iota
plus
phi
E
plus E minus iota phi, which will give you the cos phi.
so it will
So
be 1
it will give you 1 by 2
alpha
alpha
cos phi.
cos phi.
Similarly, we can
Similarly, we
the
can
value of
calculate the value of
x1
x1
square.
square.
So 1 by
So 1 by 4
alpha
alpha
A
AA
plus A
plus
dagger
AA dagger
plus A dagger
plus
A.
A dagger A.
So now A
So now A dagger is 1.
so A
So
dagger
A dagger is equals to 1 plus A dagger A.
so
So
1 by
1 by 4
alpha square.
alpha square.
So when
So when
A will
A
2
will
times
2 times
A
A will act on
give
alpha,
the
it will give you the alpha
alpha
square.
square
Alpha square
plus
plus 1
plus
plus
alpha alpha
alpha alpha star,
and then plus
and then plus
alpha
alpha
star
star
A dagger.
square when A dagger will act.
So now
So now it will give us 1 by 4
alpha plus
alpha
alpha
plus
star
alpha star
whole square
whole square
plus 1.
plus 1.
So
So
delta x
delta x1 is equals
1
to 1 by 2.
by substitute the value
Substitute the values alpha
alpha
plus
star
alpha
whole
star
square
whole square
plus 1
plus 1
minus
minus
x1 square
x1
that is
square,
alpha
that is alpha
plus alpha star
plus alpha star square,
that will give you
that will give you
1 by 2.
1 by 2.
So it means
So it means
x1
delta x1
delta x2
delta
equals
x2
to
is
1
equals
by
to
4.
1 by 4.
This is what we
This
proved
is
that
what we
it is
proved, that it is the coherent state is the minimum
state
uncertainty state,
and the
and the
uncertainty
uncertainty product of
operator
two
is 1 by 4.
operators is 1 by 4,
And it's the minimum
and it's the
uncertainty.
minimum uncertainty state.
So
So
what does it mean?
what does mean?
Vacuum and
So
coherent
vacuum and
states are
coherent
a minimum
states are a minimum
uncertainty state.
uncertainty state.
In coherent
And
state, the
coherent
quantum
state is the
analog
quantum analog
of
of the classical
electromagnetic
electromagnetic field,
field and field
and
amplitude
field
corresponds
amplitude
to the alpha
corresponds to
that
the
is a
alpha, that is a
complex
complex
quantity.
phasor quantity.
Large alpha
Large
is
alpha
large number
means large number of
which will
photons, which will represent the classical behavior.
so now
So now
we'll deal
we
with
will
the
deal with the
quantum light
quantum light, that that Henry Brown twist experiment, HPT experiment.
so quantum
So
light
quantum light.
quantum light
Quantum light has significance
has
beyond pure
pure
science. It
practical
enables
capabilities.
practical capabilities.
So first is
First is
what was the
what was the
experimental setup
experimental
that is
setup, that is
light is coming.
light is coming.
There's one beam
There's one
splitter,
beam splitter,
E1,
E1,
So G2
So G2
at time 0
at
is
time
given
0
by
is given by n minus n into n minus 1 n square.
so suppose
So suppose n and
G2.
G2 0.
So if n is
So
equal
if
to
n is equals to
G2 is
1,
equals to
G2 is equals to
if n
0.
is equal
If
to
n
2,
is equals
it
to
is
2, it
1 by
is
2.
1 by 2.
If n is
If
equals to
n
3,
is
it
equals
will
to
2 by
3,
3.
it will 2 by 3.
So now we can
So now we can
as
see
the n
that as the
increases,
n
G2
increases,
approaches
G2
1.
approaches 1.
So on the
So
basis
on
of
the basis of
G2,
G2,
we can
we
give
can
us good
give a
signature of
good
the single
signature of the
photon.
single photon.
So now we will
So now we will
deal with the
deal with the
applications of the
applications of the
quantum light. In
quantum
the
light. So in the
com- classical
in
computing,
classical
we deal with
computing,
the
we
zeros
deal
and
with the
ones.
zeros and ones.
So
So
these are the
these are the
deterministic
deterministic
quantities when
quantities
the voltage
when
is
the voltage
precise
is precise
and
and
very effective for
very effective
simple
for
logic
simple
operation,
logic
but
operation,
limited
but limited
for the
for the multi
multi-variable of the
variable or
complex
the
systems.
complex
So
systems. So
like what are
like what is
so
so
where
where
there is a
there
dependence
is a
on a
dependence
large
on a
number of
large
factors.
number of factors.
So suppose if
So
we have
suppose if
a
we are
climate
doing the climate
rainfall
modeling or
prediction
rainfall prediction
or
or
neural network
neural network
simulation, so
simulations,
then
so then
the problem
the
becomes
problem
complex.
becomes the
For the
complex.
modeling
For the
complex
modeling
system, we
complex
need
system, we need
supercomputers.
supercomputers.
For super
For
for
super for
supercomputers also some
supercomputers also some
problems takes
problems
months,
takes
years.
months, years.
So
So
if we have
if we have
so even
so even
supercomputers require
supercomputers require large amount
time
of
for the
time
complex
for the
simulation.
complex simulation.
So many
So many
analyzes
analysis relies on
approximations
approximations such
such
as
as
our
harmonic
harmonic
oscillator
oscillator
models.
models.
So Richard
So
Feynman
Richard
in
Feynman in
1982 proposed
1982
that
proposed that
classical computers
classical or
cannot
computers
efficiently
cannot
simulate the
efficiently
quantum
simulate the
system.
quantum system.
So
So
quantum hardware is
quantum
required
hardware
to
is required
accurately
to
model
accurately model
intrinsically quantum
intrinsically
phenomena.
quantum phenomena.
So if we have
So
a
if we
quantum
have a
system,
quantum
we
system, we
can't use
can't
classical
use
means to
classical
solve it,
means
so
to
we
solve
need
it.
to
So we
build a
need to
quantum
build
hardware.
quantum hardware.
So for
So for
example,
example,
MOSFET was proposed
MOSFET
in the
was proposed in the
1920s, but it
1920s, but it
realized in the
realized in the
1950s.
1950s.
So now we
So now
want to
we
develop a
want to
hardware
develop
which
a hardware which
is expected
is
for
expected
practical
for practical quantum
computing after
computing after
many years.
many years.
So
So
one protocol
one
was classical
so
encryption
classical
was
encryption
RSA.
was RSA.
So
So
RSA algorithm
RSA
is widely
algorithm is
used for
widely
secure
for secure
digital
digital
communication.
communication.
So it was
So
based
it
on
was
the
based on the
public key
public key
encryption.
encryption.
So there is a
So
public
there's a
key and
public key
private key.
and private
So
key.
the key
So the key
consists of the two
consists of
prime
the two
numbers,
prime numbers,
and
and
if we
if
multiply
we
them,
multiply them
and then
and will
the product
the
we will
product we will
announce.
announce.
So basically,
So
public key
basically,
will be the
public key
product
will be
of
the
two
product
large
of two
prime
large
numbers,
prime
and the
numbers,
private
and
key
the
is the
private key
two
is the
original
two
prime.
original prime.
So
So
security relies on
security
the
relies on the
computational difficulty
computational
of the
difficulty
prime
of the prime
factorization. So
factorization.
what we will
So
do?
what we will do?
So we will
So we will
encrypt the data in
encrypt the
public
data in
key,
public
and
key, and
for the
for
decryption
the
of the
decryption of the
information, we need to
information we need to
factorize.
factorize.
So if
So
prime
if
number will be
prime
very
number
very
will be very
large, the
very large, the
factorization will be very
factorization will be
complex
very complex
and compute.
and compute.
So
So
so the
so
classical
the
factorization.
classical factorization.
So in computer
So in
science,
computer science,
there
there
are two
are
types of.
two types of.
So there are
So there
problem
are
is
problem is
polynomial and
polynomial and
non-polynomial type. That is
non-polynomial type. That
NP
is
and P.
NP and P.
So the complexity
So
of
the
the problem
complexity of the
increases with
problem
N.
increases with n.
So
So
weak
with
encryption,
weak encryption,
powerful
powerful
computers can encrypt the
computers can
data,
encrypt the
can
data,
decrypt the data.
can decrypt the data.
But there are
But
another
there
class
are
of
another
problem which
class
are
of
called
problem which
NP.
are called NP.
So what does this
So what
mean?
does this mean?
So if we
So if
have
we have
size of the
size of the
numbers, this
numbers
is
and this is
representing F.
representing f.
So
So
the
the
Polynomial problem is
Polynomial
called
problem is
the N4.
corresponding to the N4.
Suppose if n is
Suppose if
increasing,
n is
then
increasing, then
fn is increasing.
fn is increasing by n4.
This is the polynomial.
This is the polynomial.
So if we have the
So if we
weak
have the weak
powerful
encryption, powerful
supercomputer,
supercomputers
we
will
get data.
decrypt the data and it is not much secure.
But now,
But now,
if we have
if
the
we have the
NP,
NP,
it has the
it
dependency
has the
of
dependency of
exponential.
exponential n.
So
So
polynomial time
polynomial
can be
time
solved
can be solvable
efficiently.
efficiently.
Non-polynomial grows
Non-polynomial grows
exponentially.
exponentially.
So
So
prime factorization
prime
is an
factorization
NP
is an
problem.
NP
It
problem
becomes
and becomes
intractable for large.
intractable for large number.
So as the
So
size of
as the
problem
size of
increases
problem
slightly,
increases
the
slightly, the
complexity of hardware
complexity of
required to
hardware
solve
required
it
to solve
increases
it increases
exponentially.
exponentially.
So similarly, the
So
example is
similarly, the
prime number
example is prime number
factorization. Because if we
factorization because if we
suppose if we are
suppose
increasing
if
the
we are
key length
increasing the
just by
key
one
length
bit,
just by
it
one
will
bit,
increase the
it will increase the
complexity
complexity
exponentially.
exponentially.
So it will
So it
be
will
it will
be
take a
it
large
will take a
time to
large
crack
time to
for the
crack
to
for the
crack the
to
key for
crack the key
supercomputer.
for supercomputer.
So now if we have the quantum
Now, if we have a
computer, it
quantum
should solve the
computer, it should
complex
solve
problems
the
also.
complex problems
We are
also.
talking about the
We are talking
superposition
about the
states.
superposition states.
Right?
Yes.
So we represented so
So we
quantum
represented
computing
so quantum
uses
computing
qubits
uses
instead of
qubits
classical
instead
states.
of classical
So
states.
a qubit
So
can
a
exist
qubit
in
can
superposition
exist in a
form psi is
superposition
equals to
form
c
phi
naught,
is equals to c naught,
zero state plus c1
zero
one
state
state.
plus c1 1 state.
If in a
So if
superposition
in
state
a
we have
superposition state
two
we
states.
have more number of states
If
to
we have
encode.
two bits, we will
So if we
have
have
four
two bits,
states.
we will have
With
four
quantum,
states.
it will
So with
increase.
quantum, it will increase the
So that will
so
enable
it
the parallel
that will enable the
computation and the
parallel
exponential
computation
state
and the
space.
exponential state space growth.
But measure, if
But
we measure the state,
measure if we
it
measure the
collapses the
state,
state, but
it
the
collapses
quantum
the state, but the
evolution
quantum
encodes
evolution
a rich
encodes
information
a rich
before the measurement.
information before
Because
the
before
measurement.
measurement,
Because
there
before
is a
measurement,
superposition of
there is a
state. After
superposition of
measurement,
state.
it is
After
collapsing
measurement,
into
it is collapsing into a single state.
so there was
So there was
Shor's
Shor's
algorithm
algorithm,
proposed
which
by
was
the Peter
proposed by
Shor,
the Peter Shor in 1994,
which allows the
which allows the
factorization
factorization
of large
of
number in
large number
polynomial
in
time
polynomial time
using the
using the
supercomputer,
supercomputer,
using the quantum
using
computer.
the quantum
So that will
computation. So
convert
that
an
will
NP
convert
problem
an
into a
NP
P
problem
problem.
into a P problem.
So what is the
So what is
implication
the
of it?
implication of it?
RSA
RSA
encryption in
encryption
principle
can
be
in
broken
principle be
using
broken
quantum
using
computers.
quantum
So
computers. So
companies
companies
such as Google,
such as
IBM, and
Google,
T are
IBM, and
developing
DB were developing
early
earlier
quantum
early
processors.
quantum processors.
So
So
the security
the
challenges
security
are
challenges are the
computing
quantum
threatens
computing
current
threatens
encryption
current
systems.
encryption systems.
Government and research
Government
groups
and
are
research
developing
groups are developing post
cryptographic
quantum
methods,
cryptographic methods,
and we want to
and we
create
want
an
to create
encryption
an
schemes
encryption
that are
schemes
resistant
that
to
are
quantum.
resistant to quantum attacks.
So,
So,
for the
for
quantum
the
communication,
quantum communication,
practical application
practical
of quantum
application of
light
quantum
is
light is
quantum key
quantum
distribution.
key distribution, that is QKD.
So, the
So
typical
the typical
communication protocol
communication
will
protocol
have
we
an
will have
Alice
a Alice
that will send
that
the
will send the
information is
information that it
acting
is
as a
acting as a transmitter.
then there is a
Then
port.
there is a Pope.
Both will
Both
receive
will
the data,
receive the data, that is
receiver,
receiver,
there will be one
and there will be
E,
one Eve,
that is a
that is a
eavesdropper which can
eavesdropper which can
decrypt our data
decrypt
before
our
reaching
data
to Bob.
before reaching to Bob.
So we have the
So
setup
we have the
like
setup
here.
like here.
We have
We have
Alice,
Alice.
there is
There
Eve,
is Eve. Bob.
The
The
information
information Alice
is a
is a
transmitter.
transmitter.
Bob is a
Bob is
receiver.
a receiver.
So the light is
So the light is
through.
passing through.
And we are
And
sending
we are sending the
light pulses.
impulses.
So Alice is
So Alice
transferring
is transferring
information
information
to Bob
to
in
Bob.
physical
In
approach.
classical approach,
Suppose we are sending.
suppose we are sending.
Suppose we are
Suppose
sending
we are
100
sending
million.
the 100 million photons. Okay.
Here we are
So
sending
here we are sending, and
using the
then
beam filter
using the beam filter,
50
50
50 50 beam filter.
50
So
beam filter. So
it will
it will
it will
divide,
50
it will 50,
half of the
half
photons,
of the photons,
50 million photons
50
will
million
go to the
photons
ball,
will go to the ball, 50 million photon will go to the
but
eve.
after
But
beam filter,
after beam
here
filter,
we are
here we are
the
using the
light
light
amplifier.
amplifier.
So what it will do,
So
it will
what it will do, it will increase
from 50 million
from
photons to
50 million
100
photons
million.
to again 100 million photons.
When the bulb
So
will
when
receive
the
that,
bow will receive the
it will receive the
information, it
100
will
million
receive the
photons.
100 million
Then it will
photons.
not get
Then
to
it
know
will
that
not get to know that
the
Eve.
same information
The
has
same
received by
information
Eve
has
also,
received by
but it
Eve
is
also,
not
but
known
it
to
is
both.
not known to bow.
Classically,
So classically,
our information.
our information can be decoded.
So to resolve
So to
this, we use
resolve
the
this, we
quantum
use
theory.
the quantum light.
So quantum
So
theory tells
quantum
us
theory
if we
tells
have
us
a
if we
quantum
have a quantum state
and it tries
and
to
you
measure
tries to
the
measure the quantum
then
state,
automatically
then
quantum
automatically
states
quantum
get
states
disturbed.
gets disturbed,
Bob and
and Bob
Alice
and Alice
will get to know
will
that
get to know
somebody
that somebody read the
not
message.
known.
That is the no cloning theorem.
So in
So
QKD we
in
will use
QKD, we will use the light sources
single or
emitting
few
single or
photons
few
per.
photons per pulse.
So that is
So that is
representing one.
representing one.
So logical
So
bit assignment
logical
is
bit
one
assignment
means
is
photon
one means
present,
photon
zero means
present,
photon
zero means
absent.
photon absent.
So any
So
interception
any interception
is
by Eve changes the
alert the
state and
communication.
alerts the communicating parties.
So for
So
that,
for
what
that, what
is required?
is required?
So
So
quantum,
quantum,
require
first of
the
all, we require
quantum
the
number
quantum number
generators,
generators,
QRNGs.
QRNGs.
So quantum
So
number
quantum number
generators
generators
generated
will
truly
generate the
quantum
truly
numbers.
quantum numbers.
These are many
These are many, there are many
processes that can
processes
generate
that
it.
can generate it.
For
For
example,
example,
the
the
spontaneous emission
spontaneous emission
is a simply a
is a
photon
simply a
emission
photon emission
by the
stimulated
vacuum
by the
state that
vacuum
is
state
truly
that is truly random.
another process
Another
is
process is
radioactive decay.
radioactive decay.
With that, if we
With that, if we encode the
then
data
send
and
with
then
the quantum
send with the
light,
quantum light,
keys have to be
keys
disturbed.
have to be
What is
disturbed. So
mean
what is mean
by
by
1
zero point 0.1 photon per pulse?
Suppose we have
Suppose we have
a stream of
a
light pulses
stream of light
which
pulses
pulse
which
width
has a pulse width of 100 picosecond,
and the power is
and the
1
power is
milliwatt.
1 milliwatt.
So how many photons?
So
It
how many
depends.
photons? It depends on pulse width.
1
So if
milliwatt
1 milliwatt
is
is
approximately 10 to the
approximately
power
10 raised to
5
power 5
photons
photons
per pulse
per
per
pulse
second.
per second.
So 100
So 100
picoseconds,
picoseconds,
approximately 10 to the
approximately
power
10
5
raised to power
photons per
5
second.
photons per second.
So what is
So
this?
what is this?
So we will
So we
attenuate
will
this pulse
attenuate this pulse
by using the
by using the
attenuators,
attenuators,
by using the beam
by
filter,
using the
so
beam
that the
filter so that the
transmitted
transmitted
photon will be
photon
lesser.
will be lesser.
So
So
if one
if
photon
one photon
in every
in
10
every
pulse
10 pulse
will represent
will
the
represent the
0.1
zero point 0.1 photon
per pulse.
per pulse.
So
So
by using
by
the
using the
random
quantum random number
generators,
generators,
single photon or
single photon or weak
light
coherent
sources
light
will
sources, we
secure
will
our
secure
optical
our
channel
optical
so that
channel
if
so that if
the
the
Eve
Eve
eavesdrops the
eavesdrops
message,
the
we
message,
can
we can
predict it.
predict it.
So,
So,
true
so
randomness
true
is
randomness
essential
is
for secure
essential for
encryption
secure
keys.
encryption keys.
Classical random number
Classical
generators
random
are the
number
pseudo
generators
random.
are the pseudo random.
Quantum number
So
generators
quantum
use
number generators
inherently
uses
random
inherently random processes.
So the truly
So
quantum
the
number
truly quantum
generators
number
will
generators
use the
will use
inherently
the
random physical
inherently random
processes
physical
such as
processes such as
spontaneous emission,
spontaneous emission,
radioactive decay,
radioactive
vacuum
decay,
decay.
vacuum fluctuations.
So this is one
So
part.
this is
Another
one
part is
part.
weak
The another
coherent
part is weak
pulses
coherent
will
pulses
consist of
that will consist of a
followed by
laser
an
followed by
intensity
an
modulator
intensity
and
modulator and
attenuator
optical attenuator
that will generate the
that will
pulses
generate the
with
pulses
less than
with
one
less
photon
than
per
one
pulse.
photon per pulse.
So which will give
So
us
which
the
will
zero
give
point
us a
0.1
zero
photon
point
per
0.1
pulse
photon
that
per
we have
pulse
already
that we have
understood the
already
mechanism.
understood the mechanism.
And in
And
QKD,
in
the
QKD, the
information will be
information will
encoded
be
based on
encoded
the
based on the
difference in phase.
difference in phase.
So information
So
is encoded
information
in
is
the phase
encoded
0
in the
or
phase
pi.
0 or pi.
So the
So
detection
the detection
outcome will depend on
outcome
the
will
phase
depend on the
difference
phase
between the
difference between the
consecutive
consecutive
pulses. It
pulses.
will
So
be
if
pi
it
out
will
of
be
phase,
pi
one
out of phase,
detector
one
will be
detector will
click,
be click,
one detector will
one
be on,
detector will be on,
and vice versa.
and vice
So
versa.
now
So now
we want
we want
to
to
integrate
integrate
all these
all
things,
these things,
quantum photonics
quantum
on a single
photonics
chip.
on a single chip.
Quantum
So
communication
quantum
system
communication system
can be
can be
implemented
implemented on
integrated photonic
integrated
chips.
photonic chips.
So what
So
it will do,
what
what
it
are the
will do, what are
benefits
the
of this?
benefits of
So
this?
it will
So it will
give the
give the
compactness,
compactness,
mechanical stability,
mechanical stability,
scalability, and
scalability,
it will reduce
and
the
it will reduce
fabrication
the
defects
fabrication
also.
defects also.
So now if
So
we will
now, if
have
we
the
will
integration
have the
of the chip
integration
that
of the
will
chips, that will
minimize the defects
minimize the
and it
defects,
will be
and
more
it will be more
robust and reliable
robust and reliable
against the vibration.
against the vibration.
So
So,
So differential
so
phase shift
differential phase
DPS
shift
QKD is a
DPS
common
QKD is a
on-chip
common
QKD scheme.
on-chip
So what are
QKD
the
scheme.
challenges in
So what
this?
are the
The
challenges in
optical
this?
fiber losses are
So optical
approximately
fiber
0.2
losses are
decibels per
approximately zero
kilometer
point
at
0.2 decibels per
1550
kilometer at
nanometer wavelength.
1550
And the
nanometer
current
wavelength.
QKD system
And
has
the current
already
QKD
achieved the
system has
transmission
already achieved the transmission
over 200 kilometer with a
over
few
200 kilometer with a few
kilobits per second kPa.
kilobits per second key
So
rate.
research is focusing
So
on
research
developing
is
quantum
focusing on
computers
developing
to
quantum
extend this
computers to
range
extend this range
by maintaining the
by
coherence
maintaining the
over a
coherence
long
over
distance
a long distance
but it's a very big
but it's a
challenge to
very
maintain
big challenge to
coherence over
maintain
long term.
coherence over long.
If
If
nonlinearity
nonlinearity
increase,
will
then there will be
increase,
mixing
then there
of
will be a
states.
mixing of states.
So
So
now
now
we have covered
we
the
have covered the
fundamentals of
fundamentals of
electromagnetic theory,
electromagnetic theory,
nanophotonics and
nanophotonics and
plasmonics, lasers,
plasmonics,
quantum
lasers,
light and its
quantum light and its
application,
application,
and we understood
and
the
we
quantum
understood the
system
quantum system
enables the
enables the
advancements in
advancements in
computing, communication,
computing,
and sensing.
communication, and sensing.
Now we will solve the
Now we
last
will solve the
assignment.
last assignment.
So all
So
the questions
all
we
the
have
questions we
already
have
derived.
already derived in the lecture.
The first
The
question
first
is
question
number
is a
operator
number
A
operator A
is given by. So
is given by. So
so that
we so
number
that a
operator
number operator
given
is
by
given by
A dagger.
a dagger A.
The option
The
C is
option
correct.
C is correct.
Next question is
Next
number
question is
state N
number state N
is the
is the
eigenvalue of
eigenvalue
Hamiltonian
of
phase of
Hamiltonian
Hamiltonian
phase of
amplitude
Hamiltonian
eigenfunction
amplitude
number of
eigenfunction
photon.
number of
So we
photon.
found
So
that
we found that
we are
when
applying
we are
H
applying
N,
Hn,
it was
it
giving us
was
n
giving
plus
us
1
n
by
plus
2
1
H
by
cross
2 h
omega
cross
n.
omega n.
It means
It means
it is satisfied
it
the
is satisfied
eigenvalue
the eigens
equation,
value equation,
and that's why n is the
and that's
eigenstate
why
of
n is the eigenstate of the
eigenfunction of the
eigenfunction
Hamiltonian.
of
So
the
option 4
Hamiltonian.
is
So
correct.
option 4 is correct.
Next question is number
Next question
operator
is number operator
is operating on n.
is operating on n.
What it will give us? It will give us a
What it will
number of
give us? It will
photons.
give us a number of photons.
Right, equals to-
Right, equals
So the option, last option is
so the
correct.
option last option is
All
correct.
we have solved this
All we have solved
problem in
this
the very beginning of
problem in the very
today's
beginning of
class.
this today's
That
class,
n
that n
number states are the
number
eigenstate of the
states are the
Hamiltonian,
eigenstate of the
and
Hamiltonian,
operator
and the number operator acting on the number
gives
state
the
will
number of
give
photons
the
in that
number
state.
of photons in that particular state.
So now ladder diagram for a
Now,
quantum
ladder
harmonic
diagram for a
oscillator is
quantum
given
harmonic
below in
oscillator is
figure
given
1.
below in figure
So we
1.
have to choose the
So we
correct
have to
pairs
choose
of
the correct
transition
pairs
subjected
of
to A
transition
dagger square.
subjected to A dagger square.
So
So
A dagger
A
square, we
dagger
saw that
square, we saw
A
that
dagger is
A dagger is
raising operator.
raising operator.
Okay. So
Okay.
if
So if
A dagger is
A dagger
applying
is
on 0,
applying on
then it
0,
was
then
giving
it
us
was giving us
1,
1,
right?
right?
If
If
A dagger is
A dagger is
applying on 1,
applying on 1,
it will
it
give
will give
root to 2.
root to 2.
So now
So
we are
now
applying
we are
2 times
applying 2 times
on 0,
on
then it
0,
will give
then
us
it will give us
root to
root to
2.
2.
Means from
Means
it
from
has
it has
there is a jump
there
of
is a
2
jump
states.
of
First,
two
it is
states.
getting
First, it is
excited to
getting
0 to
excited to
1,
0 to
1.
1, 1.
When A dagger is
When A
applied
dagger is
once,
applied
then
once, then
if we will
if we
again
will again
apply the A
apply
dagger,
the
it
A
will move
dagger,
to the
it will
other
move to
state.
the other
So
state.
now we
So
have
now
to
we
check
have to check
where it is
where it is
moving,
moving
there is a
where
jump
there is
by
a
2
jump
states.
by two
So if you
states.
will check
So if you will
A,
check A,
it is moving
it is moving
to the
to
excited
the
state,
excited state,
but just by a
but
single
just by
step.
a single step.
When we will see
When we
B,
will see B,
it is jumped by
it is
2. So
jumped
B
by
is
2.
the
So
correct.
B is the correct option.
There is a jump by
There is
3
a
states.
jump by
So
3 states.
it will
It
correspond
will
to A
correspond
dagger
to
3
A
times,
dagger
not A
3
dagger
times,
2.
not A dagger 2.
And all
And all the
D, E, F
D, E, F
are
are
going down in the state.
going
It is
down in the
a,
state.
there
So it
is
is a there is
annihilation is happening here,
annihilation
not
is happening here, not
creation.
creation.
So now we have to
So
choose
now
the
we have
correct
to
pair
choose the
of
correct pair
transition
of
subjected to
transition
operation
subjected
E.
to operation A.
So when
So
A will
when
operate on
A will
one,
operate on one,
it will give us
it
the
will give us the
lower state. That's
lower
why it
state.
is a
That's why
lowering
it is a
operator.
lowering operator.
Since we have to
Since
check
we have to check
it is
it is
operating once,
operating
so
once,
the
so the
down
down
downfall of the
downfall
state
of the
will be
state
by
will be
step one.
by step one.
So we'll check.
So we'll check.
So in the
So
D,
in the D,
there is step by
there is
one,
step by one,
E also, but
E
F
also, but
is
F
the
is a
decreasing of the state
decreasing of the state
by two steps.
by two
So
steps.
D and
So
E are
D
the.
and E are the correct option.
Next question is
Next
choose the
question is
correct
choose the correct
combinations for a given
combinations
number
for a
of
given
state
number of
n.
state n,
Its wave
its
functions
wave
In
functions
and
In and
eigenenergy
eigenenergy
En.
En. Mm.
So we know that
So
the
we know that
ground
the for the
state
ground state
we have the
we have the
eigenset psi naught
eigenset
and
psi naught and the
ground
energy
state
ground
energy
state energy is
half h cross omega.
half h cross omega.
So the first option
So the
is
first option is
because it is
incorrect because it
not
is
giving the
not
ground
giving
state.
the
It is the
ground
first
state. It is the
excited
first
state.
excited
And
state.
this is
And
correct.
this is correct.
And for the ground
And for
state,
the ground state,
we have the
we
energy,
have the
this
energy,
energy for the first
this
excited
energy for
state,
the first
not for the
excited
ground
state,
state.
not for the ground state.
Okay, this is
Okay, this is E.
when n is equals to
When
1,
n
then
is
only
equals to 1, then only it will be
3 by 2 h cross omega.
3 by 2 h cross omega.
So it means
Then,
it is correct
so it means
1
it is correct
psi
1
is equals to
psi
3
1
by 2
is
h cross.
equals to 3 by 2 h cross
We
omega.
can generalize it
So we can
for
generalize it
nth state
that for nth state,
psi n is
psi
equals to
n is equals to
n plus 1 by
n
2
plus
h
1 by
cross omega.
2 h cross omega.
So the option
So the option
B is
B is
correct,
correct,
D is
D is
correct, and
correct,
then
and
F,
then
E
and
is correct.
E is
So
correct.
here they
So
have
here they have
wrong.
representing the wrong eigenstate.
Next is given
Next
below
is
are
given
two
below are
statements
two
in regard
statements
to
in
properties
regard to
of photon
properties of photon
states.
number states.
So statement
So
one is
statement one is
when
when
n
n
expectation
expectation
that
the
when A will
when A
acting
will
on n,
acting on
n
n
A
A
n.
n.
So when A
So
will act
when
on
A will act
n,
on n, it will
n
give you n
root n
root n
minus.
and n minus 1.
So this is the
So this is the
Kronecker
Kronecker
delta
delta and Deshan. It is
autonomous state.
orthonormal
It
state.
is zero
It
if
is 0
n
if
is
n
equal
dash
to
is
n.
not equals to n.
So here it is
So here it is
n is not equals
n
to
is not
minus
equals
1.
to n minus 1.
It will be
So it
0.
will be 0.
Then it is given that
Then it is
n
given that
and
n and
n
n
minus 1
minus 1 are
are orthonormal.
orthonormal.
If these are
If these are
orthonormal, then only we
orthonormal,
can
then
say
only
that
we
n
can say
minus
that
1
n
is
and
0.
minus 1
So the statement
0.
S1
So
is
the
true,
statement
S1
S1 is
implies
true
S2.
and S1 implies S2.
So the option C
So
is
option
correct.
C is correct.
Next is
Next is
coherent state with a
coherent state is a
superposition. So
superposition. So
we saw that
we
coherent
saw that
state is a
coherent state is the
superposition of
superposition of
number states.
number states.
Because what will
Because what we write
alpha is equals
alpha is
to
equals to
exponential minus
exponential
mod
minus
of alpha square by
mod of
2
alpha square by 2
summation of n
summation of
is
n
equal
is
to
equals to 0
infinity
to infinity
alpha n
alpha n upon
factorial
root n factorial
n states. So this
n
is
states. So this is
what is this representing?
what is this
This is
representing?
representing
This is representing a
superposition of the number
Superposition
states.
of the number
And
states.
here it was
And here it was
normalization,
normalization constant.
and this was
And this was
coefficient
coefficient
associated with
associated with
each state.
each state.
So we can say that the
So we can
coherent
say that the coherent state is a
of the number
superposition of the
states.
number states.
Next question is
Next
coherent
question is
state
coherent
alpha is
state
an
alpha
eigenfunction.
is an eigenfunction of
We saw that
E. We saw that
alpha is not an eigenfunction of
alpha is not
Hamiltonian,
an
it was
eigenfunction of
eigenfunction.
Hamiltonian, it was an eigenfunction of
The option
annihilation
is
operator.
correct.
So the option B is
Now
correct.
state whether the given
Now state
statement is
whether the
true.
given statement is
Coherent
true or
states have
false.
many
Coherent state
uncertainties.
has many
True, we have
uncertainty.
proved
True, we
several.
have proved several times.
The next question
The
is
next question is
number phase
number
uncertainty
phase
relation
uncertainty
tells that
relation
it is
tells
not
that it is
possible to
not
know
possible to know
the photon number
the
and the
photon
phase
number
of a
and the
wave
phase of a wave
with perfect
with
precision
perfect
at the same
precision
time.
at the
It is
same time.
captured
It
by
is
which of the
captured by
following.
which of the following
So
expression?
we saw that there
We
is
saw that there
an
is an
uncertainty relation
uncertainty relation
the
between
number and
the
phase
number
axis
and
that
phase
is given
axis
by
that is given by
delta n
delta n
delta phi
delta phi
is greater than 1
is
equals
greater
to
than
1
1
by 2.
equals to 1 by 2.
So if we have the
So if
large
we
number
have
of
the large number
photons,
of photons,
phase will be
phase will be
indeterminate.
indeterminate.
Quantum computers can
Quantum computers
outperform
can
conventional
outperform
computers in
conventional
solving
computers
problems
in
with
solving problems with
arithmetic geometrics. So we
arithmetic
saw that there
geometrics.
is
So we
two
saw
types of
that there is
problem,
two types of
polynomial and
problem,
non-polynomial,
polynomial and non-polynomial,
P and NP.
P and
And in
NP.
case of
And in case of
the NP
the
problem,
NP problem,
where the size the
where the size the
where
where
there is a
there is a
if there is an
if there
increment
is an
in a bit by
increment in a
one, the
bit by one,
complexity was
the
increased
complexity was increased
exponentially. So in
exponentially.
that case,
So in
quantum
that case, quantum
computers can
computers
outperform
can
conventional.
outperform the conventional
So
computers.
the correct
So
answer is
the correct
NP.
answer is NP.
The next question
The
is the
next question is
widely
the
used
widely
RSA
used
encryption
RSA
scheme is
encryption
considered to
scheme
be
is considered
secure
to be secure
because the
because
public key
the
is the
public key is
product of
the
two large
product of
prime
two
numbers
large
which
prime numbers
comprises the
which comprises
private
the
key known
private key
only to the
known
user.
only to the user.
Yes. So
Yes.
RSA
So
encryption,
RSA
what it
encryption,
was then,
what it was
there
then.
was a
So there
public
was a
key
public key
and there was a
and there
private
was a
key.
private key.
So
So
public key
public key
was the
was the
product of
product of
two large prime
two large
numbers
prime numbers
and the
and the
private key,
private key,
the two
the two
primes
primes
numbers
numbers
were known to the
were
user.
known to the user.
So the first option
So
is
the first
correct.
option is correct.
Next statement is the
Next
public
statement
key
is
is
the
the product
public
of
key is
two
the
large
product
prime
of two
numbers
large
which
prime numbers
comprises
which
the private key known
comprises the private key
to
known to
everybody. So the private key
everybody.
is
So the
not
private
known
key
to
is
everybody, it
not
is
known
known
to
to the
everybody,
user.
it is known to the user only.
The third
The
statement
third
is the time taken
statement is
to
the
find the
time taken to
prime
find the
factors of a
prime
large
factors of a
integer
large
decreases
integer
exponentially
decreases
with the number of
exponentially with the
bits.
number of
It's a
bits.
wrong statement.
It's a wrong
Increases
statement. It increases
exponentially, not
exponentially, not
decreases. So the
decreases.
graph
So
was
the graph
n
was
f
n
n. It
f
was
n.
increasing like
It was
this.
increased like this.
The last statement is the
The
time
last
taken to
statement is
find
the time taken to find
prime
prime
factors of a
numbers.
large
Prime
integer
factors of a
increases
large integer
exponentially with the
increases
number of
exponentially with the
digits.
number of
Yes, so with the
digits.
number of
Yes,
digits,
so with the number of digits,
prime factors
the prime
of a
factors
large integer
of a
increases
large integer
exponentially. So the
increases
option A and B
exponentially.
are
So the
correct.
option A and D are correct.
The 14,
The 14,
the Nobel Prize in
the
Physics
Nobel Prize in
2022 is
Physics
awarded to.
2022 is
It
awarded
was
to.
awarded to
So it
Andrei
was
Gide
awarded to
and
Andrei Giem and
Constantinian
Daniel
Novoselov.
Novoselov. The option
So it was given
Sorry,
to
it was given
alien
to
aspect John F.
alien
Clauser
aspect
and
John F.
Anton.
Clauser and Anton.
So because they
So
have
because they have
demonstrated the
demonstrated the
potentials to
potentials to
investigate the
investigate
control,
the control,
so they have
so they have
demonstrated
demonstrated
the
the
potential to
potential to
investigate
investigate
and
and
control
control
the
the
particles
particles
that are in
that are in
entangled states.
entangled states.
The Nobel Prize
The Nobel
in
Prize in Physics
2022
2022
is awarded for
is awarded for the
experiments with invisible
experiments
photons
with
in
invisible
binary
photons,
quantum
binary
information
quantum
science. The option
information
D is
science.
correct.
The option D is correct.
So this was all about
So this was all about
this lecture.
this lecture.
So in this course,
So in this course,
we have
we have
we started with the
we started with
introduction
the
of EM
introduction
waves,
of EM
dispersion,
waves,
diffraction limit. Then
dispersion,
we moved to
diffraction
the
limit.
optical
Then we
properties
moved
of
to the optical
materials,
properties of
where we
materials,
defined the metals and
where we defined the
dielectrics.
metals and
Then we dealt
dielectrics.
with the optical
Then we
properties
dealt
of
with
low
the
dimensional
optical properties of
systems,
low dimensional
then
systems,
plasmonics,
then
LSPR,
plasmonics, LSPR,
SPP, then
SPP,
behavior of
then
electromagnetic waves
behavior
in
of
periodic
electromagnetic waves
structures,
in
then
periodic
in the block
structures, then
theorem,
define the block
then
theorem,
the materials and
then the
metasurfaces.
materials and
Then we
metasurfaces,
discussed about
then we discussed about
active
active
metamaterials,
metamaterials,
atom cavity
atom
interaction,
cavity interaction, and
nanofabrication. Then
nanofabrication.
in the
Then
last, in the past four
in the
weeks,
past 4 weeks,
we dealt with the
we
photon
dealt with the photon
statistics,
statistics,
coherent states,
coherent states,
squeeze states, and
squeeze
quantum
states, and
harmonic
quantum
oscillator
harmonic
solution.
oscillator solution.
And
And
today we discussed
today we
about
discussed
the
about
photon number
the
and
photon
coherent
number
state
and coherent
application.
state
How can
application,
we
and how
imply the
can we imply
QKD,
the
or
QKD, or where is the importance of the quantum light
in quantum
in quantum
communication.
communication.
So thank you.
So thank you.
It was all
It
about
was
this.
all about this course.